Hello everyone. In this video, we are going to talk about chapter 14, section 14.4. Continue with our material from the previous video. Then this video, we're going to learn to determine the power generated by a machine, engine, or motor. We're going to calculate the mechanical efficiency of a machine. Power, starting with the definition, power is defined as the amount of work performed per unit of time. And really, intuitively, what it means is just how fast I can do the work, right? The faster you can do some work, the higher power that we have. So if a machine or engine performs a certain amount of work du within a given time interval dt, the power generated can be calculated using this equation P equals du over dt. Since the work can be expressed, du work will be force times distance, right? So du equals FDR. Power equation can be rewritten as FDR over dt, and then if I put that dr and dt, dr over dt together, if I put this portion together, that will give me the velocity. So in other words, another way of calculating the power will be force times velocity. So power is a scalar defined as the product of force and velocity components acting in the same direction. Keep in mind that they need to be in the same direction. Using the scalar notation, power can be written as P equals FV cosine theta, where theta is the angle between the force and velocity vectors. So if the velocity of a body acted on by a force F is known, if we know the force, the power can be determined by calculating the dot product or by multiplying the force and velocity component. Unit of power in the SI system is watts, where 1 watt equals 1 joule per second. That will be 1 Newton times meter per second. In the FPS system, power is usually expressed in the units of horsepower, where 1 horsepower equals 550 feet-pound per second, divided by or this is equivalent, 1 horsepower is equivalent to 746 watts. Mechanical efficiency of a machine is the ratio of the useful power produced, output power, to power supplied to the machine, input power. So the E, mechanical efficiency, will be power output divided by power input. If the energy input and removal occur at the same time, efficiency may also be expressed in terms of ratio of output energy to input energy. So in other words, this E can also be energy output divided by energy input. Machines will always have friction force. There's frictions always there. So since frictional force dissipate energy, so sometimes it becomes the heat, your machine becomes hotter and dissipates into the air. So under that condition, right, additional power will be required to overcome these forces. Consequently, the efficiency of a machine is always less than one. Procedure for analysis: when you're running into problems like this, for step number one will always be drawing your free body diagram. Find the resultant external force acting on the body causing its motion. Second step, determine the velocity of the point on the body at which the force is applied. Energy methods or equation of motion and appropriate kinematic relations may be necessary. Number three, we're going to multiply force magnitude by the component of velocity acting in the direction of F to determine the power supplied to the body. So in other words, you have P equals FV cosine theta. That cosine theta is saying, hey, they need to be on the same direction. If they're not in the same direction, I'm taking the force and the velocity on the same direction to be multiplied together. In some cases, power may be found by calculating the work done per unit of time, P equals du over dt. If the mechanical efficiency of the machine is known, either the power input or output can be determined. Let's take a look at some examples together. So I have here block A, right? There's this motor on the right, and the motor has an efficiency of zero point 0.8. At this instant, point P, the cable has a velocity of 12 meters per second, which is increasing at the rate of 6 meters per second square. So I know my velocity, I know my acceleration. We're going to neglect the mass of the pulleys in the cable. We're going to find the power supplied to the motor at this instant. So We're gonna first write our equation for our dependent motion. We know the total length of the cable is a constant, so that's SP plus 2SA equal to L, total distance, total length of the cable. And then we're gonna take first derivative gives our velocity, second derivative gives us the relationship of the acceleration of that point P and point A. So you have AA equals negative AP divided by 2. That will be negative 3 meters per second square, or 3 meters per second square direction going up. Free body diagram. For block A, you have the weight coming down. Since there are two cables, cable number 1, cable number 2, since there are two cables pulling the block A, that will be 2T going up. And then there's the MAAA for the block A. Okay, tension of the cable can be obtained by applying the equation of motion to the block. So your FV equals MAAA. So for the total summation of all the forces being applied to the block A will be 2T, two of the tension pulling up, and the weight comes down. So you have a negative weight comes down. And then right hand side of the equation, you will be MAAA, that will be 50 times 3. We know 50 is the kilogram, how the mass of the block, and then times 3, that would be, hold on, times 3, that would be acceleration of it, where we calculated from the previous slide. Okay, putting that together, we can calculate the tension of the cable, which will be 320.3 Newton. And then next one, we're going to calculate the power supplied by the motor. So power supplied by the motor will be the product of the force multiplied by the velocity of that cable at that instant. So we know the tension of the cable calculated from the previous step, and then we're going to calculate the velocity. Velocity is given to us in our problem, 12 meters per second. So plug that in, that will give us the power supplied by the motor. And then lastly, we're looking for looking for the power supply to the motor. So in other words, we know the definition of efficiency, right? Efficiency, as you recall from here, is power output divided by power input, or energy output over energy input, right? So if we know the efficiency is zero point 0.8, we know the power output PO is 3844. We can calculate the power input, which is this much, 4,804 watts, which also 4.8 kilowatt. Next example here. So we have a sports car, increases speed uniformly. So that means constant acceleration. We know the mass, we know the constant acceleration. It's starting from rest. That means the initial velocity 0 to 25 meters per second, final velocity in 30 seconds. The engine efficiency we know is 0 0.8. We're looking for the maximum power, average power supplied by the engine. Okay, so first thing first, free body diagram. We have the weight, the friction force, the normal force being perpendicular to the surface. And then the kinetic diagram, MA, would just be mass times acceleration. Writing our equation along the x direction, notice that x direction will be parallel to the inclined plane. So you have negative, it's negative because when I break that weight into the x component and the y component, the x component is pointing toward the left. That's why it's negative. So you have negative 2000, and then times g times it's only the sine theta. Theta is 5.711. It's the sine theta portion of the what is it called? Of the total weight. Okay, and then you have the friction force plus Fc equals ma 2000 times ax on the right hand side. We can calculate the value of A. We know that this thing starting from rest, we know initial velocity, we know final velocity, we know how much time does it take going from 0 to 25 meters per second. Okay, so that means we can calculate the acceleration using the initial velocity, final velocity, and the time. Okay, we calculate the acceleration, and then we plug into the previous equation that will help us figure out the friction force. Friction force is 3,619 Newton. Next thing, if I know the friction force and we know the maximum velocity, which is 25 meters per second, right? Friction force and V max, that will give us the power output max power output. And then if I doing the velocity, right? Initially we have 0, maximum we got 25. Taking the average of this two, 0 plus 25 divided by 2, taking the average velocity average multiplied by the FC, that will give me the average power output. Okay, maximum velocity times the force gives me the maximum output. Average velocity times the force gives me the average power output. And then lastly, since we know the efficiency, plug into our equation that will help us calculate the P in max and P in average, input maximum and input average. Okay, that's all I want to share with you in this video. Hope you find it helpful. Thank you for watching.